Hello, good afternoon. This is Dr. Rafael Quintero Arcaya, who's going to be talking today about one of the most peculiar phenomena in physics and very wide applications, and that's called circular motion. And it has quite a few applications. It can be either because you are looking at satellites, natural or artificial. It could be a, a beautiful dancer, a ballet dancer just spinning around, or this very daring athletic biker who is turning around. So we're going to see how the physics behind it. In this very first video, we're just discussing the physics behind this motion in a very particular situation. And the objective is to identify the centripetal force as the force making objects turn. That's what we're going to deal with. As a reference, we have this book. There are many, but we are pointing out Giancoli physics book, and these are you have the code there to find it. Next, you say, well, Mr. Quintero, but you say we're talking about circular motion, but I already know about motion that is curved, and that's true. We have the case, for example, here that we have this athlete is skiing, and then it's being launched from some kind of a platform, and yes, it's gonna draw some kind of, it's gonna trace some kind of a curve. And we are familiar with that, okay? Now, there are quite a few things that we need to remember. Look, we have an object that is moving at constant velocity. It's gonna stay there forever unless there is a force that acts on it, okay? And that's called just the force of inertia. And that reminds us of the case of the fox and the hound. In the fox and the hound, one of them is they are just looking at the landscape from a high point, and then one of them says, "We are going to be friends forever," and the other one says, "Yes, forever." Okay, so that's pretty much what would happen to this particle, this object, if it is at constant speed. In order to introduce the phenomena of circular motion, we're going to make an assumption, and the assumption is. And let's look back a little bit. So we have the initial velocity here, and now we're applying weight. I went ahead of myself, so I'm going back. So we have that initial velocity, and now we have weight. But weight points always down, always, always. Okay. So in that case, as we are already familiar with, we see that it's going to trace a parabolic curve. It's going to be a parabolic motion. And we know all about that. We've already covered the equations that describe this type of motion. So we're going to start from that and just want to build upon a little bit on what is uniform circular motion. And in order to do that, look, this is what we're going to assume. We're going to assume that we have an object that is moving at constant speed. That is, the magnitude of the velocity vector is constant. And once in a while, at a constant pace, we're going to be applying a force. And that force is going to be normal to that velocity. When that happens, we're going to tilt it. It's going to be bent in some direction. And unless we apply the force again, it's going to keep moving in that direction. So we're saying that we're keeping the speed constant. The velocity is changing direction. The magnitude remaining constant. Since the velocity vector is changing, the acceleration is non-zero. So there is acceleration, even though the magnitude, the speed is constant. So if we do that, remember, we're doing this at constant pace. So after a while, we do it again. So this is pretty much like you having a friend and he's not feeling well or something like that, and he pats you on the back every so many steps. Pop, pop, pop. It would be something like that. And in this case, the force is acting again over here. So the velocity vector is going to change direction, even though the magnitude is being kept constant. If you do that again, look, you're essentially almost going 90 degrees from the initial position. So you are indeed changing direction. If we keep doing that, look, for the next one, we are in this point, now aiming towards the bottom, going in this direction, down south here. would be southwest in that case. And now we get the picture that if we keep continuing, if we could keep doing this, we're going to essentially come back to the same point, essentially going back to the original point. So you see that this is kind of circular. It's not perfect because I've done it manually, and all vectors are not either identical or not always, they were not always at 90 degrees. But we do get a circular path, kind of a circular path. What is very interesting is the following. Look, if we take just kind of in the middle of it and we trace a normal to it, a ray that is normal to that direction, this is what we get. Look at this. Now we have that. We do it again. Look how the rays start to coincide in one point. We do it, if we do that for all the others, the ones that are very critical, you would say, but it seems like they joined in one point here, in another there, and in another there. And that's true. That's because the circle is not perfect. But if we imagine that we are doing this in a perfect circle, we would find kind of a locus, okay? And that would be the point at which all these rays are joining, the point where they are all crossing. So that would be the center of the circle. So look, essentially what we're saying is that the object traces a circular path because the force is directed towards the center of the circle. What we've done is that we're seeing that if this particle is moving around this circle at constant speed, the velocity is changing, there must be a force that is directed always towards the center of the circle. So we're having that, and that's what we call the centripetal force. And we say that this is uniform circular motion because the speed is constant. We constructed this circle by assuming that the speed was constant, and that's how we get this circle. Now we have a force that is aiming towards the center, and we have a particle that is just moving in that circle as such. So this is pretty much the idea of centripetal force, a force that is always directed towards the circle that the particle is tracing, the object is tracing, and the velocity, yes, the velocity is always 90 degrees towards the center, towards this radius. So that's why we call, and what is important about this case? Because, look, in the case of centripetal force, there is a very nice expression, and actually it's a very simple one. It says that in the case of the acceleration, we talk about the acceleration, if we multiply that by the mass, we're gonna get the net force. And in that case, what we have is the following. Look, we have the acceleration, then it's just the square of the velocity divided by the radius. This is an expression that can be derived and is the object of another video that we have further along. The point is that if we know the acceleration, which is given by this expression, the square of the velocity divided by the radius, then we may compute the force, the centripetal force, and that's going to be the net force also. So the centripetal force is the force, the net force that makes this particle go around in a uniform way at a constant speed around a circle of radius r. And the force is going to be equal to the mass times the square of the velocity divided by the radius. This situation occurs very often in very important situations in physics, in science, in our universe. Of course, we're familiar with the case of planets moving around the sun or the moon moving around Earth. That would be one case. And we already mentioned several others. And we're going to be applying these concepts. We're going to be recognizing the force that is being applied, and then we're going to be able to compute the acceleration, and from there, the force that is exerted so that this particle remains confined to this circle at a constant velocity, at a constant speed, actually at a constant speed. We'll discuss a little bit more about that in the next video. From now on, what I would like you to understand is that we have identified the centripetal force as the force making objects turn around a circle at constant speed. And we have that the acceleration, we just stated it, you need to believe it until you see the derivation that we have in another video, that acceleration goes as the square of the velocity, just the magnitude, which is the speed, we already mentioned it, divided by the radius. And since we know that Newton's second law, the force, the net force, the one that is driving this particle around, is going to be equal to the mass times that acceleration. And in this case, it's just the square of the velocity divided by the radius. So I'm hoping that we can continue discussing this very beautiful and very interesting phenomena of uniform circular motion, and I'll see you on the next video. Let me just close by just showing you a beautiful scene of these athletes in one of the Winter Olympics just in 2018. And as you see, this is a snapshot, but they are just spinning that they were taking just at the moment they were in the air. And a beautiful, graceful application of what we are discussing today. Thanks very much for watching, and we'll see you in the next video.